Thank you for the introduction, and thank you, Professor Zhang, for the invitation to this wonderful symposium. Today, I will talk about what we have understand so far on the so-called resting state network. As many of you already know, that we're looking at a very slow synchronous neural oscillation or correlation across in the brain during the resting state or the task-free state. And is typically detected by resting state fMRI, but also can be detected by other methods. And what draws a lot of interest is that it's informed a lot of information of how the brain is organized. For example, the sensory area, visual, somatosensory, auditory, motor area, language, or other area like attention, and electric control, deformal network, and so on. And most importantly, it has been shown that this resting state network that change with brain development, brain state, neuroplasticity, aging, disease, or intervention. And especially is largely inspired by this seminal work that found the deformal network is attenuated by Alzheimer's disease. However, even almost 20 years so far, we still not clear what's the neural basis of this resting state network is, and does it do to our brain, and what's the mechanism during the disease process. So the research focus of the lab is to try to understand that neural mechanism and its functional role in terms of learning and memory, and the dysfunction in disorder, and approach for intervening the network. And we choose rodent as a model system because it has a simpler brain and with similar function and behavior like human or primate. And it has short lifespan, so you can easily do longitudinal aging study, and with a lot of transgenic and genetic tools like optogenetics available in this model, so it could be a powerful approach. And of course, it's much cheaper than primates. And so today I will cover an overview of what's the organization of the resting state network in the rodents, and talk about anesthesia effect in our study, and how we can manipulate the network, covering using drug, behavior, changing the structural connectivity, or using brain stimulation. And I will mention an example of neurodegenerative disease model. And most of the topics is covered in our recent review paper in the NeuroImage. So I will talk a lot about others' work, but I will also introduce our own work. Unlike the human study, the resting state network in the rodent was only being established in the past 10 years. So this is the first work on the rat resting state network. They show a very classical bilateral connectivity in the somatosensory area and the striatum. And we also demonstrate the first mouse resting state network that show the bilateral symmetric connectivity in the sensory cortex, subcortical, striatal, hippocampal, thalamus, and also visual cortex. So this is very exciting. We see the similar organization. And if you compare to the human, we can see a lot of similarity that you can see very bilateral symmetric network. But there's also some network that is probably more unique to the rodents. For example, the peripheral cortex, which is the olfactory cortex of the rodent, it's much stronger, whereas you don't see that in the human because rodent relies on that more. And another interesting network that probably not seen much in human is the anterior-posterior connectivity along the midline that mostly center around the cingulate cortex and the retrospinal cortex, which people have associated that is probably analogous to the anterior cingulate and posterior cingulate in human. And since we can detect that, how about the so-called deformal network that has been centered around these two areas? And indeed, there are large-scale networks like default neural network can be detected in rodents. So this is the work by Yi-Hong Yang's group that demonstrates that there are very similar topological organization of the default neural network can be detected in rat and centered around the retrospinal cortex. And also recently can be replicated in the mouse brain as well, although slightly different. However, the problem is that topological similarity doesn't mean they are functionally similar. So what's the default neural network in the rodent do? So in the beginning, we all just talk about it like default neural-like network, not default neural network. So to understand its function, in this work by Jennifer Lee, they use the oxygenation sensor implant to the awake behaving rat and show that the default neural network connectivity can be suppressed during a queued reward task. Okay. However, the somatosensory cortex, they call it lateral cortical network, is not affected. So it seems like similar to the human default neural network that's being suppressed during the goal-oriented task. Recently, we also show that when the animal, after the animal trained by the water maze task, which is a spatial memory task, the default neural network activity or connectivity is enhanced and is diminished after a week. So it seems to be consistent with the idea that default neural network is involved in memory consolidation. And recently, by again Yi-Hong Yang's group, they show that in the aged animal, they can differentiate that there are cognitively impaired rat and unimpaired rat, and they show that the retrospinal connectivity is correlate with their behavior. Okay. So it seems to indicate that the default neural network may serve similar function like in human. And another large-scale network has been identified in rodent is the salience network that centers around the insular cortex. And so the C point is put here. Okay. However, so you can see very similar kind of organization that involved in the dorsal anterior cingulate cortex, striatum, and so on. But still, we don't know what it does in the rodent brain, so it need to be investigated. And also, other kind of large-scale network, for example, the executive control network, hasn't been identified in rodent. So work needs to be done. And also, we have people have shown that the functional connectivity could reveal strength difference. Okay. So in this example is a spontaneous hypertensive rat. They are from the Vista rat background, but they build up a hypertension spontaneously. So if we look at their default neural network, they seem to have a much enhanced default neural network hyperconnectivity, which may be related to the ADHD type of behavior in this hypertensive rat. And another study from Marcus Luding's group, they show that the functional connectivity is different in different mouse strain, and the connectivity strength is related to their structural connectivity measured by FA in the corpus callosum. However, in this study, they also show that if you turn up the anesthesia isoferrin level, the spontaneous hypertensive rat have a much rapid reduction of default neural network connectivity. So it seems like this strength difference could also be modulated by their sensitivity to anesthesia. So anesthesia is an important part of our rodent study, and maybe also other primate study. So I will mention a few common anesthesia we have been using. Isoferrin is the most common one that provides general anesthesia and rapid action, people like to use it, but it drastically reduce neural activity and neural synchrony dosage dependently. So we show that in this example, when you increase the isoform level from 1% to 3%, you almost silent the evoked response, and you see a correspondence in the bow signal. And in a resting state, you also see that at 3%, you almost knock out all the neural oscillation. And similarly, you see a dramatic reduction in the functional connectivity. However, a very important feature of isoform is that around 2% you start to elicitate a so-called bursting suppression activity, which you can also see that in this EEG trace, that there's bursting and a stopping activity and then bursting again. So this is very induced in the whole brain. So if you measure the resting state around that dose, you can start to see a globally increased functional connectivity, which is just due to the anesthesia effect. And also, isoform has a vascular effect that is a vasodilator that increases CBF, but we know that with increased blood flow, your bow response will reduce. And so that's why usually you get much lower bow signal. And the anesthesia effect is also age dependent, so at younger age you would need to reduce your dose. And as we showed in the previous slide, it could also be strength dependent. And another drug we usually use, particularly our lab and many other labs, that is use medetomidine, which is a specific alpha-2-adrenergic agonist. We use it as a sedative. And in this work, we demonstrate that when you increase the sedative dose, it actually didn't increase the somatosensory activation. So the activation is not affected. But when you look at the resting state network, you can see a dramatic reduction of bilateral connectivity. And from the both signal trace, you can clearly see that it becomes synchronous. And we confirm that using electrophysiology that this dosage dependency doesn't change the neurovascular coupling. So what we're seeing is not due to a change in the vascular response, and it truly reflects a reduction, suppression of the gamma synchrony, which has been suggested to coordinate the cortical communication. So, but this drug also has a certain vascular factor effect, and which is the vasoconstrictor. So it works opposite to the isoform, which also help probably boost the bow response. And the trouble is that it has a short action period. So usually you have to do your experiment fast. And it also has a strength dependency. So in our preliminary study, we found that, for example, the FVB mouse doesn't respond to medetomidine at all. So then we changed to use this combination with low level of isoform, which is typically less than 0.5%. And this combination helped to overcome several of limitation in medetomidine. For example, if you have medetomidine for a long period, you probably see some elliptic activity. And with adding isoform, it will suppress that. And also the strength dependency we found previously in different strain of mouse is gone. Right. And people have also shown that you can sedate the animal for a long period, up to 3 hours. However, you try not to detect your activity during the first 30 minutes because the drug effect is not stable yet. And however, the problem is the thalamocortical connectivity is still suppressed. So this is due to multiple factors because isoform itself can suppress thalamocortical connectivity. Medetomidine itself also acts on thalamus a lot. And another feature is that the frequency of the spontaneous response could shift. Okay, so in this paper, they show that when you have medetomidine, your response could shift to around 0.2 Hz. So you have to be careful not to set your cutoff frequency too low. Since there are so many complications in the anesthetized rodent, so people are trying to do a awake setup. So for example, you have to put the animal within a restrainer or implant a head post and train the animal to adapt and not to move much during a loud MR scan. So if you can succeed to adapt your rat to that, you can see a much stronger increase in the cortical and subcortical connectivity, particularly between striatum and thalamus. So you can construct a resting state network that is almost covering the whole brain. And it has been shown that the anti-correlation has been interesting feature in human can be enhanced during the awake. And also if you look at dynamic connectivity, and you can see more dynamic states. However, there are still a lot of argument about whether the rodent that's being adapted, or they are just give up to against the strain. So it could be a chronic depression. Okay. So there could be more work need to be done to really develop a truly awake, happy rat. So in the following, I will introduce some of the work that how to manipulate the network. And first is to use drugs that target to the neurotransmitter system, and on glutaminergic, GABAergic, adrenergic, cholinergic, dopaminergic, serotoninergic system that's been demonstrated in the rodents. However, doing drug study, you have to be very, very careful about the central versus peripheral effect, because almost all of these drugs act on the vascular system, so you get a confound from your broad response. And also the interaction with anesthesia will be an issue. So I'll give you two examples that we modulate. One is the adrenergic system that we show that you can suppress the functional connectivity time dependently by the agonist and enhance the connectivity by the antagonist. And this connectivity change is also regional dependent, so you can see much larger suppression in the thalamus compared to almost no change in the caudate putamen. And this is really receptor density dependent, so if you compare to the known receptor distribution, you can see that thalamus has much higher receptor density compared to cortex and lower in the caudate putamen. So it's a nice demonstration that functional connectivity potentially can reflect neurotransmission action. And we also look at how the GABAergic system, which is so essential in the brain, and we use the antagonist called bitupilin, which suppresses the GABA action. And we see a large increase of the long-range cortical connectivity compared to, so this example we have CPON at the somatosensory cortex, and you can see that the connectivity now extends to the visual cortex. And however, this connectivity change doesn't correlate with the CBF increase, which we have been also used, suggested by pharmacological MRI study that this response could be mimicked to the receptor density distribution that can be shown in this picture as well, that thalamus has much higher receptor density. However, this you don't see any thalamic connectivity getting enhanced. So this may not reflect the local receptor distribution, but maybe mediated by the excitatory connectivity, long-range projection that is modulating. And another factor is this antagonist may counteract the isoferrin effect, but we show that using electrophysiology, there's no sign of it's increasing the spontaneous activity. Okay. So it shows that the modulating the neurotransmission system could elicit differential effect at different sites. And next, we were looking at how you can manipulate the network by behavior. So we train the animal in the so-called Morris water maze. So you have a visual cue on the wall, and you train the animal to recognize there's a particular hidden platform that he can escape from water at a certain corner. So over 5 days of training, you can see the rat learn very well. And if you look at the functional connectivity, if you just train the animal for 1 day, they didn't learn, they're still fooling around in the pool, and you don't see much connectivity. And with 5-day well-trained rat, you can see that the rat swings straight to the platform, and you see a dramatic increase of functional connectivity, now talking to the hippocampus. And if you track if we try to track the same animal over 1 week, and you see the functional connectivity now start to migrate and toward the cortex. So it seems to demonstrate that the functional connectivity may reflect the learning and maybe memory consolidation. And we also show that the anesthesia, the sedative we use, which doesn't affect the memory, because we know adrenergic agonists can affect memory consolidation. So if we, then we are thinking whether we can enhance the functional connectivity by modulating the neurotransmitter. So we use donepezil, which increases the acetylcholine level, has been used as a treatment for dementia. And by giving 2 weeks of donepezil, we can see an enhanced functional connectivity centered around coated glutamen, and you can compare to the binding site of this drug is also high density in the coated glutamen. And the drug really worked to boost the memory in the animal. And if we correlate the learning performance and the functional connectivity before the learning, and we found that retrospinal connectivity is very strongly correlated with the learning behavior. So it seems to implicate that this could be a target area important for this learning capacity, and maybe an area for modulating that. So if we want to modulate a structural connectivity, previously people just cut the corpus callosum to see whether the structural connectivity really underlies these functional connectivity. And with complete callosotomy or partial callosotomy, where they just cut the posterior part, and indeed they show that there's loss of bilateral connectivity. Interestingly, they show that 1 month later, the partial callosotomy group have the connectivity come back, and which also been consistent with the EEG recording. So what it shows that even losing the axonal direct projection, the functional connectivity could still find a way to reroute. We modulate the connectivity in a slightly different way. We use a toxin called cuprizone that's used to damage oligodendrocyte. So you feed the animal for 6 weeks under cuprizone, you can see a gradual demyelination, also seen in T2-weighted MRI. If you remove the toxin, and the myelination come back. So it's go through another remyelination process. And when we look at the evoked response and the resting state connectivity, we didn't see much of bilateral connectivity change. However, we did see a drastic increase of ball response during the demyelination period, which probably due to the increased neuroinflammation during that period. Another group using similar model, they also show that the functional connectivity actually not changing much. However, by demyelination, they lose the structural and functional correlation. And being able to image the mouse, people have started to compare to the monosynetic projection atlas provided by the Allen brain. So this is an example from Marcus Luding's group. They compare to the ingestion site using it as a C point for functional connectivity analysis. You can see very nicely overlap of the structure and functional connectivity. And they also use this metrics to come up with a way to try to predict functional connectivity based on the axonal projection. And you can get reasonably good estimate in the neocortex or the striatum, but not in the thalamus. Probably because the anesthesia just suppressed the thalamic connectivity. Also, for the large-scale network like deformal network, and compared to the ingestion site in the anterior cingulate, you don't see a good overlap. So that may indicate that the large-scale network is going through a polysynetic projection. In our mouse, we also show that these structural connectivity strongly correlate with functional connectivity strength. However, it didn't correlate with other measure of connectivity like amplitude of low frequency fluctuation or structural covariance. So if we want to modulate the network, I think the better way is to do brain stimulation like I just showed. So this group from North Carolina show that using deep brain stimulation you can activate or inhibit the downstream pathway. However, this stimulation only induces a transient change in the connectivity. If you look at the resting state network, it didn't change. However, the same group also showed that if you stimulate by optogenetics, you only see the ingestion site. You don't see the other area being activated. So probably the deep brain stimulation is activating fibers in other direction, not the efferent area. So optogenetics is a powerful way that you can express light-sensitive neuron in certain area and even certain cell type. So Edwards groups show that if you activate the BPN, which project to the sensory cortex, you can get very nice evo response. However, if you tune the stimulation to a very low frequency that's close to what we see in the resting state, but now they just use 1 Hertz, you see a very different pattern. You now see a bilateral activation and in the visual cortex, which is quite surprising. And they can show that if you measure the resting state connectivity, the connectivity was enhanced not only during the optogenetic stimulation, but after the stimulation is turned off and is increased. And in the recent paper, they further show that if you modulate, you should stimulate the also danger drivers with low frequency compared to high frequency, you see a very different region being activated. For example, in this case, if you stimulate by 0.5 Hertz, you activate the visual cortex, visual pathway from LGN, superior colliculus, and V1, not just the hippocampus. And again, the connectivity getting enhanced also after the stimulation. And they further show that if you now give visual stimulation, the visual activation get upregulated. So it indicates that the slow oscillation may change the gain of the visual response, and it's not through the area we typically think. It's through some other area like hippocampus. Another way to modulate the pathway or network is by using so-called DREAD and activated by a drug called CNO. And in recently, people just showed that yes, you can activate certain pathway specifically, but it didn't seem to change the functional connectivity in the resting state. However, it could be a very powerful technique to combine it with the behavior and inhibiting certain network hub. So in this work, in the mouse, they use the CFOS, not the resting state fMRI, to construct this network after field conditioning learning. And they identify network hub that if you remove that hub, it could change the whole network construction. So they identify 21 hubs and start to inhibit those area by DREAD. And they found 4 areas show very nice behavioral change. And they found that the global efficiency of those networks correlate with the animal behavior. So indicate that network hub could really have a very important behavior role.
Time.
Right. So I would just probably jump to our recent work on Huntington disease. So we also look at the Huntington disease as a model system. Right. All right. So we try to understand the conflicting result in human that some show increase or decrease functional connectivity in the Huntington patient. So we look at the Huntington mouse. We found that the somatosensory network is being suppressed in the Huntington disease, and we can recover some of the connectivity by giving memantine to suppress the excitotoxicity. And since then the change in the somatosensory network, sensory motor network, but not the hippocampal or deformal network, seems to be in line with the behavior that we see much larger change in the motor behavior compared to novel object recognition. We also compare that to the structural covariance network that seems to correlate well with functional connectivity, and in the disease, this correlation is suppressed. So in conclusion, rodent could be a very nice translation model because it shows very similar, not only topological, but probably functional organization. And be careful about the anesthesia. We can modulate the brain network with many different ways. And the model system can give us insight to the particular pathological effect. So, but there are still questions remain how the disease spread and whether we can target to certain network to intervene. And I'd like to thank all the collaborators and people helping on this work, and thank you for your attention.
Thank you very much for this very comprehensive and good overview about resting state in rodents. One very quick question. If there are no questions, then yeah, make it short.
Yeah, sure. Did you try to look at effective connectivity when you were comparing axonal connections with function connectivity? To try to distinguish direct and indirect connections?
Yeah, that's a very excellent idea and approach that I just talked to Professor Park about how to do that. So hopefully we can show you something next time.
So next speaker then